Right now, at this very moment, tiny fragments of ancient worlds are quietly burning up in the atmosphere above you, creating gentle streaks of light that most of us never see. These cosmic whispers have been falling to Earth for billions of years, carrying stories from the very beginning of our solar system. Welcome to Sleep About Science. Tonight, we're exploring the peaceful world of meteors, means those gentle celestial visitors that paint brief, beautiful lines across our night sky. And if you drift off to sleep while listening, that's perfectly wonderful. In fact, meteors themselves are nature's own lullaby, appearing and disappearing in soft, silent arcs overhead. Before we begin, please make yourself comfortable. Pull up your blankets, settle into your pillow, and let your breathing slow. Remember, this is educational content, not medical advice. If you haven't subscribed yet, you might want to, so you never miss these gentle journeys into science. Now, wherever you are in the world, whether it's evening where you're listening, or perhaps you're drifting towards sleep at dawn, imagine looking up at the vast dark canvas of space above us. Every single day, our planet catches about 100 tons of space dust and small particles. Most of these cosmic visitors are no larger than grains of sand, yet they create some of the most beautiful light shows in nature. The word meteor comes from the Greek word meteors, meaning high in the air. How perfectly fitting for these atmospheric dancers. When we see a meteor, we're actually witnessing the final moments of a tiny piece of cosmic material, perhaps a fragment that broke away from a comet millions of years ago, or a small chip of asteroid that has been wandering through space since the early days of our solar system. Picture this: a meteoroid, no bigger than a pebble, has been traveling through the emptiness of space for countless years. It has felt no air, heard no sound, experienced no friction. It has been in a state of perfect silent motion, following the gentle gravitational pulls of planets and stars, and then suddenly it encounters something it has never experienced before, mined to our atmosphere. At speeds between 11 and 72 kilometers per second, this tiny traveler begins to compress the air in front of it. The air cannot move out of the way fast enough, so it becomes superheated, glowing with temperatures that can reach over 3,000 degrees Celsius. Yet paradoxically, the meteoroid itself often remains relatively cool inside, like a stone in a campfire that's hot on the outside but unchanged within. Most meteors burn up completely between 80 and 120 kilometers above our heads. That's higher than where airplanes fly, higher than weather balloons drift, in that thin, quiet realm where Earth's atmosphere gradually gives way to the emptiness of space. Up there, in that peaceful transition zone, these cosmic visitors spend their final moments creating light. The light we see isn't actually the meteoroid burning, it's the air around it glowing from the intense heat. The colors depend on which elements are present in the meteoroid and the surrounding atmosphere. Iron creates yellow and orange glows, magnesium burns blue-white, sodium produces an orange-yellow light, and nickel glows green. It's like a gentle chemistry experiment happening silently above us every night. On any clear, dark night, if you lie back and watch the sky with patience, you can expect to see about 6 meteors per hour. They appear randomly, these cosmic fireflies, painting brief brushstrokes of light across the darkness. Each one represents a story millions or billions of years in the making, concluding in a few seconds of gentle radiance. During meteor showers, this peaceful display becomes more frequent. Shower meteors aren't random visitors. They're the scattered debris of comets that visited our inner solar system long ago. As comets orbit the sun, they leave trails of dust and small particles behind them, like breadcrumbs marking their path through space. When Earth's orbit carries us through these trails, we encounter higher concentrations of meteoroids, and the gentle light show intensifies. The Perseids, visible each August, come from the comet Swift-Tuttle, which last visited the inner solar system in 1992. The comet itself won't return until 2126. But its gifts keep giving, mind you, every year. Earth passes through the stream of particles it left behind, and we're treated to up to 60 meteors per hour during the shower's peak. The Geminids in December come from an asteroid called 3200 Phaethon. This is unusual. Most meteor showers originate from comets, but the Geminids show us that asteroids too can leave trails of debris for us to discover. The particles that create Geminid meteors are often denser than comet debris, so they tend to create brighter, more colorful streaks as they burn up. Imagine the Leonids, which peak each November. These meteors appear to radiate from the constellation Leo, and they come from comet Tempel-Tuttle. Every 33 years or so, when the comet returns to the inner solar system and refreshes its debris trail, The Leonids can produce meteor storms of thousands of meteors per hour, creating a gentle cosmic blizzard of light. The radiant point, the area of sky from which shower meteors appear to originate, is simply a perspective effect. The meteoroids in a shower are actually traveling in parallel paths through space, but from our viewpoint on Earth they seem to diverge from a single point, like looking down a long straight road where the parallel edges appear to meet at the horizon. Most meteoroids are incredibly small. The ones that create visible meteors are typically between the size of a grain of sand and a small pebble. Something the size of a grape can create a fireball bright enough to read by. The tiniest ones, barely larger than dust motes, create meteors so faint they're invisible to the naked eye, though sensitive cameras can detect them. When a meteoroid is large enough to survive its journey through the atmosphere and reach the ground, it becomes a meteorite. This is rare. Most meteoroids are too small to survive the intense heating of atmospheric entry, but those that do make it become precious gifts from space, carrying information about conditions in the early solar system. Scientists estimate that only about one meteoroid in 1,000 is large enough to produce a meteorite. The rest give their entire existence to creating those few seconds of gentle light. There's something beautifully selfless about this minutiae. These ancient travelers, having journeyed for so long through the darkness, spend themselves completely in a brief moment of radiance. The atmosphere protects us so effectively that even meteoroids the size of basketballs typically burn up completely before reaching the surface. The few that make it through intact are usually quite small by the time they land, perhaps the size of a walnut or smaller. They fall to Earth at terminal velocity, no longer blazing with heat, often cool enough to touch within minutes of landing. Meteorites are categorized into three main types. Stony meteorites, the most common, are made primarily of silicate minerals and often contain tiny spherules called chondrules, nodes, droplets of molten rock that formed in the early solar system and never melted again. Iron meteorites are composed mostly of iron-nickel alloy and are thought to come from the cores of ancient asteroids that were large enough to differentiate into layers, like miniature planets. Stony iron meteorites, the rarest type, contain both rocky material and metallic iron-nickel. Some meteorites are older than Earth itself. They formed in the disk of gas and dust that surrounded our young sun over 4.5 billion years ago. When you hold a meteorite, you're touching material that predates our planet's formation, matter that witnessed the birth of the solar system. The largest meteorite ever found is the Hoba meteorite in Namibia. It weighs about 60 tons and is thought to have fallen to Earth around 80,000 years ago. Despite its enormous size, it created no crater. It likely entered the atmosphere at a relatively shallow angle and had slowed to terminal velocity by the time it reached the ground. It sits there still, a gentle giant resting peacefully in the African landscape. Antarctica is one of the best places on Earth to find meteorites. The ice preserves them beautifully, and the white landscape makes the dark stones easy to spot. Scientists have recovered tens of thousands of meteorites from Antarctica, including some from Mars and the Moon. These Martian and lunar meteorites were blasted off their homeworlds by asteroid impacts millions of years ago and eventually found their way to Earth. The Moon has no atmosphere to burn up incoming meteoroids, so its surface is covered with impact craters of all sizes. Every visible crater on the Moon tells the story of a cosmic collision. The dark patches we see on the Moon, called maria or seas, are actually vast plains of hardened lava that filled in some of the largest impact basins billions of years ago. Meteoroids can travel through space for millions or even billions of years before encountering Earth. During this time, they're exposed to cosmic radiation, which creates unique isotopes within the material. By studying these isotopes, scientists can determine how long a meteoroid traveled through space before becoming a meteorite. The speed at which meteoroids enter Earth's atmosphere depends on the relative motion between the meteoroid and our planet. Earth orbits the Sun at about 30 kilometers per second. Meteoroids can be traveling in the same direction as Earth, in which case the relative speed is lower, or they can be approaching head-on, creating much higher relative speeds and brighter meteors. When a very bright meteor appears, monish bright enough to cast shadows or be visible during daylight, it's called a fireball. Exceptionally bright fireballs, brighter than the planet Venus, are sometimes called bolides. These spectacular events are rare but unforgettable. The meteor that exploded over Chelyabinsk, Russia in 2013 was seen by countless people and was bright enough to temporarily outshine the sun. The Chelyabinsk meteor entered the atmosphere at about 19 kilometers per second and exploded at an altitude of 23 kilometers. The shockwave from the explosion broke windows across the city, but remarkably, no one was seriously injured. The event reminded us that we live in a dynamic solar system where cosmic encounters, while rare, are part of the natural order. Most meteor impacts on Earth go unnoticed. Our planet is mostly covered by oceans, and much of the land is sparsely populated. Scientists estimate that several meteorites larger than a kilogram fall to Earth each day, but the vast majority are never recovered. They rest quietly in forests, deserts, and ocean floors, holding their cosmic secrets. The sound of a bright fireball often reaches observers minutes after the visual event. This delayed sound can be a distant rumble, like thunder, or sometimes sharp cracks and booms. The sound is created by the shock waves generated as the meteoroid pushes through the atmosphere, but unlike the light, which travels at the speed of light, sound moves much more slowly through air. Some observers report hearing strange swooshing or sizzling sounds simultaneously with very bright meteors. This phenomenon, called electrophonic sound, is still not fully understood. It may be related to electromagnetic pulses generated by the meteor interacting with objects near the observer, causing them to vibrate and create audible sounds. Meteors have been inspiring human imagination for thousands of years. Ancient cultures often interpreted them as messages from gods or omens of significant events. The word fireball itself speaks to our ancestors' attempts to understand these celestial visitors. Today we know them as natural phenomena, but they retain their capacity to inspire wonder and remind us of our place in the cosmos. The Quadrantid's meteor shower each January is named after an obsolete constellation called Quadrans Muralis. The constellation is no longer officially recognized, but the meteor shower keeps its name, a gentle reminder of how our understanding of the night sky has evolved over time. Light pollution has made meteors less visible to many people today. In a brightly lit city, you might see only the brightest meteors, while the same sky viewed from a dark location could reveal dozens per hour. The gentle streaks of light that our ancestors took for granted now require a journey away from city lights to fully appreciate. Radio waves can detect meteors even during daylight hours or cloudy weather. As meteoroids burn up in the atmosphere, they create ionized trails that reflect radio signals. Amateur radio operators often use these brief reflections to bounce signals farther than would normally be possible, a technique called meteor scatter communication. The peak viewing time for meteors is typically between midnight and dawn. This is when your location on Earth is facing forward in Earth's orbital motion around the Sun, like looking through the windshield of a car driving through a swarm of insects. During evening hours, you're on the trailing side of Earth, seeing only the faster meteoroids that can catch up to our planet. Meteors appear brightest when viewed overhead, where they travel through the thickest part of the atmosphere. Near the horizon, meteors often appear dimmer and may seem to move more slowly, though this is partly an optical illusion caused by perspective. The color of a meteor can sometimes tell you about its composition, but it's also influenced by the speed at which it enters the atmosphere. Very fast meteors tend to appear blue or white, while slower ones often look red or orange. The most common colors are yellow and white, created by the heating of atmospheric gases and the meteor's own material. Occasionally, a meteor will leave a persistent trail in the sky, visible for several minutes after the meteor itself has vanished. These trains are made of ionized gas that continues to glow as it slowly disperses. They're most commonly seen with bright fireballs and can sometimes be observed changing shape as high-altitude winds blow them across the sky. The study of meteors, called meteoritics, has contributed enormously to our understanding of the solar system. Meteorites provide direct samples of asteroids, comets, and even other planets without the need for expensive space missions. They're like cosmic mail, delivering scientific information directly to our doorstep. Some meteorites contain organic compounds, including amino acids, the building blocks of proteins. This doesn't mean they carried life to Earth, but it suggests that the chemical processes that led to life may be more common in the universe than we once thought. These cosmic chemistry sets may have contributed to the ingredients available on early Earth. Presolar grains, minute particles that formed around other stars before our solar system existed, have been found in some meteorites. These ancient specks of stardust are older than the Sun itself, formed in the atmospheres of dying stars and blown into space by stellar winds. They represent the recycled material from which our entire solar system formed. The asteroid belt, located between Mars and Jupiter, is the source of many meteorites. This region contains remnants from the early solar system that never coalesced into a planet, possibly due to Jupiter's gravitational influence. These asteroids occasionally collide with each other, sending fragments on new trajectories that may eventually intersect with Earth's orbit. Comets, often called dirty snowballs, are mixtures of ice, dust, and rocky material that formed in the cold outer regions of the solar system. As they approach the sun, the heat causes their ices to sublimate, creating the beautiful tails we occasionally see and leaving behind trails of debris that become meteor showers. The Oort cloud, a spherical shell of icy objects surrounding our solar system at distances up to 100,000 times farther from the Sun than Earth, is thought to be the source of long-period comets. These distant visitors may take thousands of years to complete a single orbit, and when they do approach the Sun, they sometimes leave gift trails of particles that can create new meteor showers. Meteoroids can originate from surprisingly diverse sources. While most come from asteroids or comets, some are actually pieces of the Moon or Mars that were blasted into space by large impacts. These planetary meteorites are extremely rare but provide invaluable opportunities to study other worlds without leaving Earth. The interplanetary dust particles that create the faintest meteors are so small they can take years to fall through Earth's atmosphere. During this long, gentle descent, they cool down and are eventually collected in the stratosphere by high-altitude aircraft or simply settle to the ground as cosmic dust. Every year, Earth gains mass from the influx of meteoric material. While individual meteoroids are tiny, the cumulative effect is substantial. Might as our planet gains thousands of tons of cosmic material annually. This has been happening throughout Earth's 4.5 billion year history, contributing to our planet's growth. The Allende meteorite, which fell in Mexico in 1969, is one of the most studied meteorites in history. It's a carbonaceous chondrite containing some of the oldest materials in the solar system, including calcium-aluminum inclusions that formed over 4.5 billion years ago. Scientists consider it a time capsule from the solar system's birth. Tektites are natural glass objects formed when large meteorite impacts melt terrestrial rock and blast it high into the atmosphere. As these molten droplets cool and solidify during their flight, they form distinctive, smooth glass objects that fall back to Earth hundreds of kilometers from the impact site. They're like Earth's own version of cosmic gifts. The Vredefort crater in South Africa, created by a meteorite impact about 2 billion years ago, is the largest verified impact structure on Earth, with a diameter of roughly 300 kilometers. Today it appears as gentle hills and valleys, worn down by 2 billion years of erosion, but it represents one of the most significant cosmic encounters in Earth's history. Meteorite impacts may have played a crucial role in the development of life on Earth. Besides possibly delivering organic compounds, impacts may have created hydrothermal systems that provided energy and chemical gradients necessary for early life. Some scientists suggest that life on Earth may have emerged in impact-generated hot springs. The famous Tunguska event of 1908 in Siberia was likely caused by a meteoroid or small comet that exploded in the atmosphere. The blast flattened trees over an area of 2,000 square kilometers but left no crater, suggesting the object disintegrated completely before reaching the ground. It remains one of the most powerful natural explosions in recorded history. Meteorite hunting has become a popular hobby and scientific pursuit. Dedicated searchers travel to desert regions where meteorites are easier to spot and better preserved. The dry conditions of deserts like the Sahara and the Australian outback help prevent meteorites from weathering away and make them more visible against the sandy background. The chances of being struck by a meteorite are extraordinarily small, estimated at about 1 in a million during a person's lifetime. You're more likely to be struck by lightning multiple times than to be hit by a meteorite. This rarity makes meteorite impacts on people noteworthy events that often make headlines when they occur. Urban legends sometimes claim that meteorites are hot when they land, but this is usually false. While they heat up intensely during their atmospheric entry, small meteorites cool quickly in the thin upper atmosphere and fall at terminal velocity for the final portion of their journey. By the time they reach the ground, they're typically at ambient temperature or even cold. The trajectory of a meteor across the sky can provide clues about its origin in the solar system. By precisely measuring the path, speed, and timing of a meteor, astronomers can sometimes calculate backward to determine which asteroid or comet it came from and trace its journey through space. Meteorites have been used by humans for thousands of years. Before iron smelting was developed, meteoritic iron was one of the few sources of workable metal. Ancient cultures crafted tools, weapons, and jewelry from meteorites, often considering them sacred objects that fell from the heavens. The word siderite, used to describe iron meteorites, comes from the Greek word for iron, sideros. Ancient Greeks believed that iron fell from the sky, and they weren't wrong. The first iron used by humans likely did come from meteorites before terrestrial iron ore was mined and smelted. Modern detection networks use automated cameras and sensors to track bright meteors across large areas. These systems can triangulate a meteor's path and predict where meteorites might have fallen, greatly increasing the chances of recovery. The speed and precision of these networks turn meteor watching into a coordinated scientific endeavor. Some meteoroids are so small they create micrometeors, mistus flashes of light visible only through sensitive equipment. These tiny particles, smaller than grains of sand, burn up at altitudes of 120 kilometers or higher and represent the most common type of meteoric event, even though we can't see them with our naked eyes. The study of isotope ratios in meteorites has revolutionized our understanding of solar system formation. Different meteorite types preserve signatures of different environments and processes from 4.5 billion years ago, creating a library of information about conditions in the early solar nebula. Chondrite meteorites come from larger asteroids that underwent geological processing like melting and differentiation. Unlike chondrites, which represent primitive solar system material, chondrites show us what happens when asteroids grow large enough to have internal heating and geological activity, like miniature planets. The famous SNC meteorites mined after Shergoti, Nokla, and Chassigny are believed to come from Mars. Their ages, around 1.3 billion years, are much younger than most meteorites, suggesting they came from a geologically active world. Gas trapped within them matches the Martian atmosphere composition measured by spacecraft. Lunar meteorites provide samples from parts of the Moon never visited by Apollo missions. These rocks, blasted from the lunar surface by impacts, eventually made their way to Earth and give us a broader picture of lunar geology and composition. The Murchison meteorite, which fell in Australia in 1969, contains over 70 different amino acids, many of which are not found in Earth life. This suggests that the basic chemistry of life might be widespread throughout the cosmos, forming naturally in space environments. Diamonds have been found in some meteorites, formed by the extreme pressures of asteroid collisions in space. These nanoscale diamonds are more ancient than any diamonds formed on Earth and provide clues about high-energy processes in the early solar system. The timing of meteor showers is remarkably consistent from year to year because Earth's orbit is so regular. The peak nights of major showers like the Perseids and Geminids can be predicted decades in advance, allowing astronomers and enthusiasts to plan viewing sessions with confidence. During a meteor shower's peak, meteors appear to radiate from a specific constellation, but they can appear anywhere in the sky. The best strategy for viewing is to look about 30–45 degrees away from the radiant point, where meteors will appear longer and more dramatic as they streak across your field of view. The speed of a meteor's apparent motion across the sky depends on several factors: its actual velocity, its angle relative to your line of sight, and its distance from you. Swift meteors might cross your field of view in less than a second, while slower ones may take several seconds to traverse the sky. Meteors contribute to the formation of noctilucent clouds, rare, high-altitude clouds that form at the edge of space. The fine dust from meteors may provide condensation nuclei for ice crystals at altitudes where normal cloud formation is impossible, creating ethereal, silvery clouds visible on summer nights. The electromagnetic effects of bright meteors can sometimes interfere with radio communications and even trigger lightning detectors. The ionized trail left by a meteor can act like a temporary antenna, creating brief but measurable electromagnetic disturbances. Micrometeorites, ASHU, extremely small particles that survive atmospheric entry, rain down constantly on Earth's surface. They're so tiny that air resistance slows them gently rather than heating them to destruction. These cosmic dust particles can be found in rainwater, on rooftops, and even in deep-sea sediments. The Leonid meteor storms of 1833 and 1966 were so intense that observers described meteors falling like snowflakes or like leaves in autumn. These spectacular displays occur roughly every 33 years, when Earth passes through the densest part of Comet Tempel-Tuttle's debris trail. Some meteorites contain water-bearing minerals, suggesting that water was present throughout the solar system during its formation. This water may have been one of the sources that helped fill Earth's oceans billions of years ago, carried here grain by grain on countless meteoroids. The angle at which a meteoroid enters Earth's atmosphere affects how long it remains visible. Shallow entries create longer, slower meteors, while steep entries produce brief, intense flashes. The optimal angle for a spectacular meteor display is around 45 degrees to the horizontal. Meteorites found in hot deserts often develop a coating called desert varnish, a dark, shiny surface formed by chemical weathering over thousands of years. This coating can help protect the interior of the meteorite from further weathering, while giving it a distinctive appearance. The concept of a shooting star is beautifully poetic, even though meteors aren't stars at all. These brief streaks of light connect us to the cosmos in the most direct way possible. They're actual visitors from space that we can witness with our own eyes, bridges between the earthbound and the celestial. Ancient Chinese astronomers kept detailed records of meteor observations, some dating back over 2,000 years. These historical records help modern scientists understand the behavior of meteor showers over long time periods and track changes in comet orbits across centuries. The fragmentation of meteoroids during atmospheric entry can create spectacular displays where a single object breaks apart into multiple glowing pieces. These fragmenting meteors often appear to sparkle or flutter as they break up, each piece following its own slightly different trajectory. Meteorites that fall on ice sheets like in Antarctica or Greenland can remain perfectly preserved for hundreds of thousands of years. The ice acts as a natural freezer, protecting organic compounds and delicate minerals that might be destroyed in warmer climates. The study of cosmic ray exposure in meteorites tells us how long they traveled through space as small objects. Cosmic rays create unique isotopes in meteoritic material, providing a clock that records the time between when a meteoroid broke off from its parent body and when it fell to Earth. Some meteor showers are so reliable that they've been observed and recorded for over 1,000 years. The Perseids, for instance, have Chinese records dating back to 36 AD, showing that this annual shower has been a consistent celestial performance for nearly 2 millennia. The terminal velocity of a small meteorite, the speed at which it falls during the final non-luminous part of its journey, is typically between 100 and 300 meters per second. This sounds fast, but it's much slower than the initial entry speed of tens of kilometers per second. Fusion crust, the thin, dark layer that forms on meteorites during atmospheric entry, is typically less than a millimeter thick. This glassy coating forms when the surface of the meteoroid melts and then quickly solidifies, creating a protective shell around the unmelted interior. The largest meteorite fall in recorded history was the L'Aigle Fall in France in 1803, which scattered about 3,000 individual stones across the countryside. This well-documented event helped convince the scientific community that rocks could indeed fall from the sky, overturning centuries of skepticism. Carbonaceous chondrites, some of the most primitive meteorites, contain organic compounds that formed in space before the solar system existed. These ancient molecular fossils provide insights into the chemical processes that occurred in interstellar space and the earliest solar system. The phenomenon of zodiacal light, a faint triangular glow sometimes visible in the western sky after sunset or eastern sky before sunrise, is caused by sunlight scattered off countless tiny particles throughout the inner solar system. These particles are the same type that create meteors when they encounter Earth's atmosphere. Meteoroids can be gravitationally captured by planets and spend years orbiting before eventually entering the atmosphere. These temporarily captured objects, sometimes called mini-moons, demonstrate the complex gravitational dance occurring throughout the solar system. The International Meteor Organization coordinates observations from amateur astronomers worldwide, creating a global network of skywatchers who contribute to our understanding of meteor phenomena. This collaboration between professionals and amateurs shows how curiosity about meteors continues to inspire people around the world. As you settle deeper into comfort tonight, perhaps under blankets that shield you from the night air, remember that above you, Earth's atmosphere serves as a gentle shield too, protecting us from the constant influx of cosmic debris while treating us to nature's own light show. Every meteor represents a story billions of years in the making, myths, ancient wanderers from the far reaches of space completing their journeys in brief moments of beautiful radiance. These cosmic visitors remind us that we're part of something much larger than our daily concerns. We live on a planet that moves through space, catching stardust and ancient fragments, participating in the slow, grand dance of the solar system. The next time you see a meteor streak across the night sky, you're witnessing not just a pretty light, but the final chapter of an epic journey that began in the earliest days of our cosmic neighborhood. The International Space Station orbits Earth at an altitude of about 400 kilometers, placing it well above the region where most meteors burn up. Astronauts aboard the station have a unique perspective on meteors, seeing them from above as they streak through the atmosphere below. From this vantage point, meteors appear as brief flashes of light in the thin shell of atmosphere that surrounds our planet, offering a reminder of how delicate and precious our atmospheric protection truly is. The Eta Aquarids meteor shower, visible each May, comes from perhaps the most famous comet of all, Halley's Comet. This ancient wanderer takes about 76 years to complete its orbit around the Sun, but the debris trail it has left behind during its many passes continues to grace our skies annually. When you watch an Aquariid meteor, you're seeing a piece of the same comet that amazed people throughout history, from ancient Chinese astronomers to European chroniclers who saw it as an omen. Halley's Comet last visited the inner solar system in 1986 and won't return until 2061. Yet every year, Earth encounters particles that this comet shed centuries or even millennia ago. There's something beautifully persistent about this mitas long after the comet itself has retreated to the cold outer reaches of the solar system. Its gifts continue to reach us, connecting us across time to this ancient celestial visitor. The speed at which meteoroids travel through space varies greatly, depending on their origin and trajectory. Those that approach Earth head-on, moving opposite to our planet's orbital direction, can have relative speeds of up to 72 kilometers per second. To put this in perspective, at this speed, you could travel from New York to Los Angeles in about a minute. Yet despite these incredible velocities, most meteoroids are so small that they burn up completely in just a few seconds of atmospheric contact. The hypersonic shock waves created by fast-moving meteors can sometimes be powerful enough to shake buildings or rattle windows, even when the meteor burns up high in the atmosphere. These shock waves travel through the air at the speed of sound, which is why the sound of a bright fireball often reaches observers several minutes after the visual event has ended. Sporadic meteors, meteors, those that don't belong to any particular shower, can appear at any time and from any direction. These random visitors make up the background rate of meteoric activity that we see every night. They represent the general population of debris scattered throughout the inner solar system, each following its own unique orbital path until it intersects with Earth. The orbit of Earth around the Sun takes us through different regions of space throughout the year, which is why different meteor showers are visible at different times. In essence, Earth acts like a cosmic vacuum cleaner, sweeping up particles as we move along our orbital path. The annual repetition of meteor showers reflects the regularity of Earth's orbit and the persistence of debris trails left by comets. Some meteoroids are so large that they can be detected by radar as they approach Earth. These house-sized objects are rare, but when they do enter the atmosphere, they can create spectacular superbolids, meteors brighter than the full moon that can be seen during daylight hours. The explosion of such an object over Russia in 2013 was detected by infrasound sensors around the world. The fragments that survive atmospheric entry and become meteorites often show signs of their violent journey. Many meteorites display regmegalips, Mias thumbprint-like, depressions on their surface created by the differential melting during atmospheric flight. These natural sculptures tell the story of each meteorite's final moments of flight through our protecting atmosphere. Oriented meteorites are particularly fascinating. These are meteoroids that maintained a stable orientation during their atmospheric flight, developing a distinctive cone-like shape with a blunt front and pointed back, like a natural bullet. The consistent airflow over their surface creates beautiful symmetrical regmegalips and a smooth fusion crust. The study of meteorite falls versus finds reveals interesting patterns about how these cosmic gifts reach us. Falls are meteorites that were observed to land and recovered quickly, while finds are meteorites discovered later, sometimes many years after they fell. Antarctic meteorites represent a special category. They're technically finds, but the ice preserves them so well that they're almost as pristine as fresh falls. Meteoroids can remain in near-Earth space for extended periods before finally encountering our atmosphere. Some follow complex trajectories, influenced by the gravitational fields of Earth, the Moon, and other planets. These orbital mechanics create a slow dance that can last months or even years before the final atmospheric encounter. The ablation process, the gradual wearing away of a meteoroid's surface during atmospheric entry, creates the beautiful light trails we see. Different materials ablate at different rates and temperatures, which is why meteors of different compositions can produce different colors and intensities of light. Iron-rich meteoroids tend to create yellow-orange trails, while those rich in magnesium produce blue-white light. Atmospheric density plays a crucial role in determining where meteors become visible and where they burn up completely. The exponential decrease in air density with altitude means that meteors typically begin to glow at around 120 kilometers altitude and usually burn out completely by 80 kilometers altitude. This narrow zone represents the transition between the near vacuum of space and the protective blanket of our atmosphere. The phenomenon of meteor trains miligus, the glowing trails that sometimes persist after a bright meteor has passed, can occasionally last for several minutes. These trains are composed of ionized gas molecules that continue to emit light as they slowly recombine and cool. High-altitude winds can cause these trains to twist and bend, creating ethereal, shifting patterns against the star field. Radio meteor detection has revealed that the meteor flux is much higher than visual observations suggest. Many meteors are too faint to see with the naked eye, or they occur during daylight hours, but they still create ionized trails that reflect radio waves. This technique has shown that Earth encounters far more meteoric material than we typically realize. The Draconid's meteor shower, associated with comet 21P/Giacobini-Zinner, is unusual because it's best viewed in the evening hours rather than before dawn. This shower occasionally produces meteor storms, though it's typically quite modest. The unpredictability of the Draconids adds an element of surprise to the annual meteor calendar. Meteorite-strewn fields, the elliptical areas where fragments from a single fall are distributed, can extend for many kilometers. The largest pieces typically fall at the far end of the strewn field, while smaller fragments are scattered throughout. Understanding these patterns helps meteorite hunters locate specimens and scientists reconstruct the atmospheric breakup process. The cosmic velocity of meteoroids entering Earth's atmosphere ranges from about 11 km per second to 72 km per second. This enormous range reflects the variety of possible orbital configurations in the solar system. Meteoroids approaching from the outer solar system generally have higher velocities than those originating from nearby asteroids. Meteorite weathering on Earth varies dramatically depending on the environment where they land. In desert environments, meteorites can remain relatively unchanged for thousands of years, developing only a thin patina of oxidation. In humid climates, iron meteorites can rust away completely within decades, while stony meteorites may disintegrate even faster. The discovery of meteorites with unusual isotopic compositions has revealed that our solar system formed from a heterogeneous mix of materials. Some meteorites contain grains that formed around other stars before our Sun existed, carrying isotopic signatures that are impossible to create in our solar system. These presolar grains are literally pieces of other star systems. Shock metamorphism in meteorites provides evidence of the violent collisions that occurred in the early solar system. High-pressure minerals found in some meteorites could only have formed during intense impact events, suggesting that the period of heavy bombardment was even more dramatic than previously thought. The concept of meteorite pairing recognizing that multiple specimens come from the same original fall has revolutionized meteorite classification. Through careful analysis of mineral composition, texture, and cosmic ray exposure ages, scientists can often determine that meteorites found kilometers apart actually come from the same parent meteoroid that broke up during atmospheric entry. Carbonaceous chondrites contain some of the most primitive materials in the solar system, including presolar diamonds smaller than viruses. These nanodiamonds formed in the atmospheres of dying stars and were blown into space by stellar winds, eventually becoming incorporated into the disk of material that formed our solar system. The extinct radionuclides found in meteorites minus radioactive elements that no longer exist naturally on Earth provide timestamps for events in the early solar system. These cosmic chronometers tell us when different types of meteorites formed and help us understand the sequence of events that led to planet formation. Some meteorites contain evidence of aqueous alteration minus chemical changes caused by liquid water on their parent asteroids. This suggests that many asteroids contain subsurface water for extended periods, creating environments where complex chemistry could occur. These water-rich asteroids may have been important sources of Earth's oceans. The texture of meteorites reveals details about their formation conditions. Chondrules morphs, the small, round inclusions found in many meteorites, appear to have formed as molten droplets in the early solar system, possibly created by shock waves or electrical discharges in the solar nebula. Each chondrule represents a snapshot of conditions 4.5 billion years ago. Meteorite falls have been recorded throughout human history, often with detailed descriptions that help modern scientists understand historic events. The Ensisheim meteorite, which fell in France in 1492, was witnessed by many people and is one of the earliest well-documented meteorite falls in Europe. The stone is still preserved today, more than 500 years later. The search for meteorites has led to some of the most remote places on Earth, from the ice fields of Antarctica to the sand seas of the Sahara. Meteorite hunters travel to harsh environments where these cosmic visitors are best preserved and most easily found. Each recovery expedition is like a treasure hunt for samples of deep space. Micrometeorites collected from urban environments show that cosmic dust falls everywhere on Earth. Researchers have found these tiny space particles on building rooftops, in rain gutters, and even in the sediment of city ponds. This constant, gentle rain of cosmic material means that every place on Earth receives a steady supply of extraterrestrial matter. The magnetic properties of meteorites often make them detectable with metal detectors, leading to the discovery of many specimens that would otherwise remain hidden. Iron meteorites are particularly easy to detect this way, as they contain large amounts of metallic iron-nickel alloy that sets them apart from terrestrial rocks. Witnessed meteorite falls create opportunities for scientists to study fresh, uncontaminated samples. When a meteorite fall is observed and specimens are recovered quickly, researchers can analyze organic compounds and other sensitive materials before they're altered by terrestrial weathering. These fresh falls are particularly valuable for understanding the original chemistry of asteroids and comets. The atmospheric entry of large meteoroids creates plasma minus-A, a state of matter where electrons are stripped from atoms by extreme heat. This plasma interacts with Earth's magnetic field and can create electromagnetic effects detectable by sensitive instruments. Very large meteors can even cause temporary disruptions in radio communications. Tektites, formed when large meteorite impacts melt terrestrial rocks and launch them into ballistic trajectories, are found in specific regions called strewn fields. These natural glass objects represent the only way that Earth rocks regularly leave the planet's surface and travel hundreds of kilometers through the atmosphere before landing again. The Tunguska event of 1908 left no crater because the incoming object, whether a comet or asteroid, exploded in the atmosphere before reaching the ground. The airburst was powerful enough to flatten trees over an area larger than a major metropolitan city, yet left no physical evidence except the destruction pattern itself. Modern meteorite classification systems recognize dozens of different types, each representing different formation environments and processes in the early solar system. From primitive chondrites that preserve the original composition of the solar nebula to highly evolved achondrites from differentiated asteroids, each type tells part of the story of planetary formation. The amino acids found in some meteorites include many that are rare or absent in Earth biology, suggesting that the chemical diversity of the early solar system was much greater than what survived on our planet. These exotic amino acids provide clues about the types of chemistry that might be possible in other worlds. Meteorites from Mars preserve atmospheric gases trapped within shot glass formed during the impact that blasted them off the red planet. Analysis of these gases matches the Martian atmosphere composition measured by spacecraft, providing definitive proof of their origin and offering insights into Martian geological history. Lunar meteorites have provided samples from the far side of the Moon and from regions never visited by Apollo missions. These rocks, excavated by impacts and launched from the lunar surface, eventually found their way to Earth and expanded our understanding of lunar geology beyond the limited areas explored by human missions. The cosmic ray exposure, ages of meteorites. The time they spent traveling through space as small objects range from less than 1 million years to over 50 million years. This tells us that the asteroid belt has been an active collisional environment throughout recent geological time, constantly generating new meteoroids through impacts. Some meteorites show evidence of multiple impact events on their parent bodies, with shock features overprinted on earlier shock features. This reveals that asteroids have experienced complex collisional histories, with some objects surviving multiple major impacts before finally being disrupted enough to send fragments toward Earth. The preservation of organic compounds in meteorites requires special storage conditions to prevent contamination and degradation. Museums and research institutions maintain these specimens in clean, controlled environments, sometimes using the same techniques developed for preserving biological samples or archaeological artifacts. Meteorite thin sections. The slices of meteorites ground to translucent thinness for microscopic study reveal internal structures invisible to the naked eye. Under polarized light, these sections display beautiful arrays of colors and textures that tell detailed stories about temperature, pressure, and chemical conditions during meteorite formation. The trace element compositions of meteorites provide fingerprints that can sometimes be matched to specific asteroid families. By comparing meteorite chemistry with spectroscopic observations of asteroids, scientists can sometimes identify the specific parent bodies from which particular meteorites originated. Meteorite orbits, calculated backward from observed falls, sometimes reveal surprising trajectories. Some meteorites have traveled well beyond the asteroid belt before encountering Earth, while others have followed complex paths involving multiple planetary encounters. Each trajectory tells a unique story of gravitational dynamics in the solar system. The study of noble gases in meteorites provides information about solar wind conditions and galactic cosmic ray bombardment over millions of years. These chemically inert gases accumulate in meteorites during their space voyage and serve as recorders of the space environment they encountered. Meteorite research has contributed to the development of new analytical techniques that benefit many fields of science. High-precision isotope analysis, advanced electron microscopy, and other methods developed for meteorite studies have found applications in materials science, environmental monitoring, and other areas of research. The distribution of meteorite falls across Earth's surface reflects our planet's protection by the atmosphere and the bias in human observation and recovery. More meteorites are found in areas with suitable geology for preservation and active searching, but the actual fall distribution is relatively uniform across the globe. As our solar system continues its journey around the galactic center, it encounters different regions of space with varying concentrations of interstellar dust and debris. Over very long timescales, this galactic environment may influence the meteoroid flux reaching Earth, connecting our planet's meteorite record to the broader cosmic environment. The silence of space gives way to the gentle whisper of atmosphere, and ancient travelers become moments of light. In this quiet transformation, there's something deeply peaceful, the idea that even endings can be beautiful, that even the smallest travelers can create moments of wonder, and that the universe continues to send us gentle reminders of our connection to the cosmos. These cosmic messengers arrive daily, most burning up unseen in the daylight hours or over remote oceans, their brief lives dedicated to creating a few seconds of radiance. They represent a form of cosmic recycling, where the debris of ancient collisions becomes new moments of beauty, where the waste products of celestial mechanics become gifts of light for anyone patient enough to watch the night sky. The meteorites that survive their atmospheric journey become permanent ambassadors from space, carrying information across billions of years and millions of kilometers to rest quietly in museum drawers and research laboratories. Each specimen is both a scientific treasure and a philosophical reminder, tangible proof that we live in a dynamic, interconnected universe where matter flows freely between worlds. In the grand scale of geological time, the current age represents a relatively quiet period for Earth's meteorite bombardment. The heavy bombardment that shaped the early solar system has subsided to a gentle, steady rain of cosmic debris. We live in a time when meteorites are scientific curiosities rather than world-shaping catastrophes, when we can appreciate their beauty and scientific value without fearing their destructive potential. Perhaps there's something comforting in knowing that this cosmic rain continues, night after night, year after year, connecting us to the broader universe in the most tangible way possible. Every meteor represents a small victory of physics over distance, a successful completion of an impossibly long journey through the emptiness of space. They remind us that even in the vast loneliness of the cosmos, we are not isolated, we are constantly receiving visitors from deep space, gentle reminders that we belong to something much larger than our daily concerns. As you drift towards sleep tonight, wherever you are in the world, remember that above you, Earth's atmosphere continues its patient work of capturing and transforming these cosmic travelers. The same protective shell that keeps you warm and breathing also serves as a canvas for one of nature's most beautiful light shows. In protecting us from the harshness of space, our atmosphere creates art from debris, light from destruction, beauty from the simple physics of matter encountering resistance. Thank you for joining me on this extended journey through the peaceful world of meteors. Whether you've drifted off during our exploration or remained alert throughout this cosmic meditation, I hope you found some measure of comfort in learning about these gentle visitors that connect us to the stars. The next time you see a shooting star, you'll know you're witnessing not just a pretty light, but the final chapter of an epic story that began billions of years ago in the outer reaches of our solar system. Sleep well, and may your dreams be filled with gentle light streaking peacefully across vast dark skies. Sweet dreams, and may your rest be as serene as ancient stardust finally finding its way home.